Welcome to The Explainer. I am so excited you're joining us today because we've got a truly fascinating topic to unpack. We're going to take a 3D journey that scales all the way from the microscopic anatomy of a single, seemingly harmless grasshopper right up to a massive, world-threatening swarm. We'll be looking closely at the biology, the life cycle, and the environmental triggers that can turn just one solitary insect into a global agricultural crisis. Let's get right into it. Okay, so let's kick things off with an absolutely wild statistic from the UN's Food and Agriculture Organization. 80 million. That is the number of locusts that can cram into just a single square kilometer during a swarm. To put that devastating scale into perspective for you, an outbreak of that density can consume enough crops in a single day to feed 35,000 people. When we're talking about global food security, this is literally one of the most immediate and destructive natural threats out there. But looking at this massive, macro-level threat, it really makes you wonder, right? How on earth does a single, isolated insect become a plague of this magnitude? Well, to find the answer, we actually have to zoom all the way in, away from the swarm, and look at the microscopic, anatomical level of a single member of the Orthoptera order. To really understand the swarm, we have to kind of mentally build the anatomy of a grasshopper. Basically, this biological machinery breaks down into three main segments. First up, you have the cephalo, or the head, and that contains the specialized mouth parts, the antennae, and those big compound eyes. Move down a bit and you hit the thorax. This is basically the engine room. It houses 3 pairs of legs and up to 2 pairs of wings. And finally, we have the abdomen, which contains all of the metabolic and reproductive organs. Together, these 3 segments are the natural machines powering every bit of the insect's feeding and movement. Now, a super critical piece of this puzzle lies in their reproductive biology. Take a female from the Titigoniidae family. You probably know them as bush crickets or katydids. During reproduction, she will actively consume a large, nutrient-rich spermatophore produced by the male. In this biological setup, the female plays a highly active role, actually ingesting these vital nutrients to directly fuel the development of the next massive generation of eggs. It's an incredibly efficient system. Chronologically, the life cycle of these insects is just incredibly structured. It all starts out as an egg, which, depending on the exact species and where it lives, often enters a state of winter pause known as embryonic diapause. Basically, it safely waits out the cold months until rising temperatures and moisture give it the signal to hatch. From there, the insect goes through 5 distinct nymph stages, which are called instars, before finally graduating into the fully developed adult phase. And the spatial growth across those instars follows this fascinating, strict progression. With every single molt, the nymph expands its body size by about a quarter. It looks more and more like a mature grasshopper with each step. But if you look closely at the wings, it's only in that final molt into the adult phase that the wings fully form and harden, finally unlocking their ability to fly. Now, if we zoom in on those fully formed wings and legs, we find the mechanism for their iconic communication, stridulation. Imagine the 3D friction required for this. The insect lifts its wings and vigorously rubs a specialized comb on its right wing against a specific ridge on its left wing, or sometimes it even rubs its leg against the wing. This mechanical friction creates that classic mating song we all associate with warm summer nights, and it's primarily used by the males to attract females. Okay, so here is the absolutely crucial point. This wild Jekyll and Hyde metamorphosis that certain grasshopper species possess. A perfect example of this is the Moroccan locust, or Dosiostratus marroconis. Normally, they exist in a solitary phase. They're just harmless, isolated individuals living their lives. But when specific conditions are met, they undergo a drastic biological shift into a gregarious phase. They literally transform their behavior and their physiology, becoming a dense, swarming, highly mobile macroorganism that aggressively goes after crops. But what actually acts as the catalyst for this terrifying transformation? Well, the data points directly to abiotic triggers, meaning physical, non-living environmental factors like unpredictable weather patterns. Think severe droughts followed by extreme rain and winds. These conditions basically force the insects to crowd together into smaller and smaller areas where there's still vegetation. And it's this physical crowding that acts as the trigger. It forces their biology to flip the switch right into that massive, uncontrollable swarm phase. Try to wrap your head around the extreme scale of these events when they scale up to a massive, multi-kilometer radius. In a true outbreak, a single swarm can consist of up to 2 billion individuals. Their total weight can range from 3,000 to an astronomical 50,000 tons. Just imagine the devastating agricultural impact of a 50,000-ton swarm landing on a farming region. As we mentioned earlier, the sheer volume of vegetation they consume can wipe out an entire local food supply overnight. So, how do we actually fight back without destroying the entire ecosystem in the process? Well, if we zoom back down into the microscopic level, we find the modern solution. Relying solely on harsh chemical insecticides often kills natural predators like birds and beneficial insects, which honestly just makes the problem worse in the long run. Instead, modern agriculture is turning to biological warfare. By using natural pathogenic bacteria like Serratia marcensis and specific entomopathogenic fungi like Beauveria bassiana, combined with cultural farming interventions, we can safely target the locusts and keep their nymph populations below the economic damage threshold. It's pretty amazing, right? We've seen how a single, solitary insect, driven by its biology and triggered by shifting weather patterns, can transform into a 50,000-ton agricultural nightmare. The delicate balance between climate, insect biology, and our farming systems has literally never been more apparent. So, as extreme weather events become more frequent, I want to leave you with this thought. How will we continue to evolve our biological defenses to protect global food security from the next inevitable swarm? Thank you so much for exploring this fascinating topic with me today. I hope you found it as engaging as I did, and I'll see you on the next explainer.